Welcome to The Explainer. Today, we're digging into Microsoft's really ambitious plan, a detailed blueprint to build a quantum computer that's actually useful and fault-tolerant. And it all kicks off by tackling the single biggest roadblock in the entire field. Okay, so let's just dive right in. Yeah, forget all the Hollywood hype for a minute. The real race in quantum computing isn't just about who can build more quantum bits or qubits. At the end of the day, it really all boils down to one single fundamental problem. So here's the thing. The very heart of the issue is that quantum information is just unbelievably delicate. The same quantum properties that give these computers their incredible power, like being in multiple states at once, also make them, well, incredibly fragile. And you can really see the difference here. The classical bits in your laptop are pretty much rock solid. They are a definite 0 or a definite 1, period. But a qubit, it exists in this kind of ghostly superposition of states, and the tiniest vibration or change in temperature, what physicists just call noise, can corrupt the information and totally wreck a calculation. Right, so the takeaway here is pretty clear. Building a powerful quantum computer isn't just about piling up more and more qubits. It's about making qubits that can survive this, like constant storm of quantum error. And this is where Microsoft's whole approach gets super interesting. See, instead of just trying to wrap these fragile qubits in the quantum equivalent of bubble wrap, Microsoft is building a completely different kind of qubit, right from the ground up, one that's designed to be naturally resistant to errors. They call it a tetron. Its whole design is based on this really exotic, almost magical idea from physics called topological protection. The information isn't stuck in one tiny vulnerable spot. Instead, it's spread out across 4 of these weird, particle-like things called Majorana zero modes. This is such a great way to think about it. Imagine your quantum information is a knot in a rope, right? You can wiggle the rope around, shake it, that's all the environmental noise. But the knot itself, that fundamental topological property, it stays put. That information, it's safe, protected by its very shape. Okay, so they have this super powerful new qubit. Now what? Well, with this new tool in hand, Microsoft has laid out a really clear step-by-step plan. Let's check out the roadmap and see exactly how they plan to build this thing, from a single piece into a full-blown computer. All right, here it is. This is the official plan, right out of their research paper. It's this multi-generational plan where they scale things up step by step, building all the necessary capabilities at each stage. You can see it moves from a single building block on the left, all the way to a complex error-correcting system on the right. So where do you start? Well, just like you'd expect, it begins with a single qubit device. I mean, you gotta walk before you can run, right? And the goal here, it sounds simple, but it is absolutely vital. They just need to prove that this basic building block, the tetron qubit, actually works the way they think it does. This means running a whole series of tests. They call it measurement-based qubit benchmarking to confirm its unique properties and prove it behaves exactly like their theories predict. So once they've proven that one works, they scale up to a 2-qubit system. This is where things start to get, computational. So with 2 of them, the goal is to show off this really key process called measurement-based braiding. What this means, basically, is that by taking a specific sequence of measurements, they can manipulate the qubit's information without ever actually touching it. That's the braiding, and that's how they'll perform the first basic logical operations, the first real step towards an actual computation. All right, Generation 3. Now we're scaling up to an array of 8 tetrons, and this is where that error-fighting superpower really starts to shine. The goal here is to show the power of quantum error detection. By spreading information across multiple physical tetrons to create a single, much tougher logical qubit, they can start to actually see when errors happen, which is a massive milestone.
And that brings us to Generation 4. The big one, a large-scale, scalable array. This is pretty much the end game.
At this point, the system is designed to be truly fault-tolerant. It's not just seeing errors anymore, it can actively go in and correct them as they pop up, using some fancy techniques called lattice surgery. And that is the breakthrough you need to build a machine that can actually solve massive real-world problems. Okay, so that's the plan, a really complex step-by-step roadmap. But what's the payoff? Why go through all this trouble to build this specific kind of topological qubit? Well, the first big win is scale. Their paper points out that you could fit millions of these tiny tetron qubits onto a single wafer. And that kind of density is absolutely key if you're going to build a machine that's truly powerful. And this brings us right back to where we started. The really crucial thing to get here is that this topological approach, it's not just a tiny improvement. It gives you an exponential reduction in errors. It's designed to solve the biggest headache in quantum computing right at the source. So what does this actually mean? Why should you care? Because this whole approach just makes everything way more practical. The controls become more digital, less fussy. Operations are lightning fast. We're talking microseconds. And at the end of the day, it could take calculations that are currently impossible, things that would take millennia, and crunch them down to just hours or days. So by focusing like a laser on building a really tough, error-resistant qubit from the get-go, this roadmap lays out a super compelling and frankly credible path to a machine that doesn't just sit in a lab, but one that can actually change the world. Which leaves us with one final thought. Could this be it? Are we looking at the actual blueprint that's finally going to unlock the quantum age?